In this talk, we're going to use the inclusion exclusion principle to count derangements. We've seen this before when we defined derangements, only we saw that derangements were very hard to count. Well, we'll see now we can do it more easily with the inclusion exclusion principle. So to count derangements, let's first get our notation straight. D sub n, capital D sub n, will denote the number of derangements of a string with n distinct letters. So we can just take the string 1, 2, 3 all the way up to n. N could be any number, any natural number. Now, for our universe here, we're going to look at the set of all rearrangements. Of this string. That's the string with n distinct letters. And it's very easy, I'll just make a quick note of that, to tell how big our universe is. The size of the universe is just n factorial. Now, of course, many of those are not derangements. So in order to count derangements, we somehow have to understand what defines a derangement. And I didn't even mention that, so let me talk about what a derangement is. A derangement of the string is a rearrangement in which no element stays in its original position. So we can think of that as saying this element 1 cannot end up in position 1. The element 2 cannot end up in position 2, etc. Well, if we're going to construct our sets so that what we want to find is the size of the intersection of the complements, we want each set to kind of say what we don't want about one of the elements. Well, we don't want 1 to end up in position 1. So set A1 will be, or A1 will be the set of all rearrangements I'll use the term which fix the element 1. That means leave element 1 in its original spot. To be a derangement, of course, our rearrangement will have to not be in A1. But moreover, we can do that for each and every element in our string. A2 will be the set of all rearrangements which fix element 2. A3 will be the same thing which fix element 3. And we'll keep going to A sub n, which will be the set of all rearrangements which fix element n. Now, with this definition of the sets A1 through AN, if a rearrangement doesn't fix any of the elements, it's called a derangement. It means exactly that. It's not in A1, not in A2, not in A3, all the way up to not in AN. That's exactly an element in this set, the intersection of A1 prime, A2 prime through AN prime. So our goal is just to count the size of this intersection, A1 prime through AN prime. And luckily, the inclusion exclusion formula tells us that D sub n, which is exactly this number, is given by S0 minus S1 plus S2 minus S3. And we'll keep going all the way till we get to S sub n, which will have plus or minus, depending on whether n is even, then there would be a plus, or n is odd, in which case there would be a minus. And we've already seen that the size of our universe is n factorial. This is just S0. Well, what is S1? S1 is the sum of the sizes of all the sets. Well, how big is each set? I claim they're all the same size, because fixing any one element gives you the same number of rearrangements as fixing any other. And how big is that? Well, we have n sets, A1 through AN. Each one has size, I claim, n factorial. And not n factorial, that's totally wrong. N minus 1 factorial, which is important, so let me write that properly. N minus 1 factorial because we've insisted, say for A1, that our rearrangements fix the element 1. We just have n minus 1 remaining elements that can be rearranged, and that can be done in n minus 1 factorial ways. The same would be true for A2. You're fixing element 2, but all the other n minus 1 elements can be arranged in n minus 1 factorial ways. So we have n minus 1 factorial elements in each of the sets, A1 through AN, the total being n times n minus 1 factorial. What is S2? Well, S2 is the sum of the sizes of the intersections of these sets taken two at a time. I claim each of those is the same. If you fix any two elements, there will always be n minus 2 factorial ways to rearrange the other n minus 2 elements. So for every pair of sets, we'll have n minus 2 factorial rearrangements in the intersection of those two sets. Now, how many pairs do we have? We have exactly n choose 2 pairs of sets, so S2 will be n choose 2 times n minus 2 factorial. And in a similar manner, S3 will have n choose 3 triples of n choose 3 ways to pick 3 sets at a time, and the size of the intersection of those will be exactly n minus 3 factorial for each triple of sets, because when you take 3 of the sets, to be in all 3, you have to fix 3 particular elements. One example would be to fix 1, 2, and 3. There are n minus 3 elements left over, and they can be rearranged in n minus 3 factorial ways. So this continues all the way to S sub n, which is n choose n times n minus n factorial. Notice this is just 1 times 1, or 1 times 0 factorial, which is precisely 1. There's only one element in the intersection of all of these sets. What does it mean to be in all of the sets? It means every element from 1 through n is fixed. The one rearrangement that does that is the rearrangement that doesn't move anything. So what is our formula for d sub n? It will just be s naught, which is n factorial, minus s1, which is n times n minus 1 factorial, plus s2, that's n choose 2 times n minus 2 factorial, minus s3. And we'll keep going like that all the way up until we get to 1, which is s sub n. Now here's the first important thing to notice. S naught is n factorial, S1 is n times n minus 1 factorial. Those will always cancel, and really we just have these terms. And so if we write it like this is what I had just written before. Remember, this last term is just 1. We can write d sub n as the sum of n choose 2 times n minus 2 factorial minus n choose 3 times n minus 3 factorial, all the way up to n choose n times 0 factorial, which is just 1. If we put that in compact notation, we can sum that from k equals 0 to it could be k equals 0 to n, but it's just as good to start with k equals 2 to n, because the 0 and the 1 term cancel. So we have the sum from k equals 2 to n of minus 1 to the k, that's the alternation in signs, times n choose k times n minus k factorial. And we have a perfectly nice formula, again, not a closed form formula, for d sub n, and this works for any number n which is at least 1 here. In fact, when n equals 1, d sub 1 is 0, so really this will make sense when n is at least 2, is what we'll say. Let's check out this formula real quickly. What is d4? d4, using this formula, is 4 choose 2, which is 6, times 4 minus 2, which is 2 factorial, that's 2, minus 4 choose 3, which is 4, times 4 minus 3, which is 1 factorial. Then we'd have the 4 choose 4 times 0 factorial, which is plus 1. That's 12 minus 4 plus 1, that's 9. And that's a number we've already seen when we first looked at derangements. There are 9 derangements of a string with 4 distinct letters. One more quick computation. What is d5? d5 is 5 choose 2, which is 10, times 5 minus 2, which is 3 factorial, which is 6, minus 5 choose 3, which is 10, times 5 minus 5 minus 3, which is 2 factorial, that's just 2. Then we'd have plus 5 choose 4, which is 5, times 1 factorial. And then we would have minus 5 choose 5 times 0 factorial, which is minus 1 at the end. This is 60 minus 20, that's 40, plus 5 minus 1 is 44. There are 44 derangements of a 5-letter string. There's 5 distinct letters in the string. Now, once we've computed d sub n, there's some fun we can have with that. First, let's ask the question, if we take a string with n distinct letters, like 1, 2, 3, 4, all the way up to n, and we pick a rearrangement at random, what is the probability that it's a derangement? Well, of course, there are n factorial rearrangements, and there are d sub n derangements, so that probability is just d sub n over n factorial. Well, this was exactly our formula for d sub n, so d sub n over n factorial is just 1 over n factorial times that formula. And I'm going to put that 1 over n factorial in here, and I'll write n choose k as n factorial over k factorial times n minus k factorial. So that's this part here. And the n minus k factorial is there. Notice that this cancels there, the n factorial cancels there, and I get left with something very simple. Just the sum from k equals 2 to n of minus 1 to the k times 1 over k factorial. That's just 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial. And we'll keep going, alternating plus and minus, until we get to plus or minus 1 over n factorial at the end. And note that there'll be a plus if n is even, a minus if n is odd. And this formula might or might not look familiar to you. Why might it look familiar? Well, you probably remember the Taylor series for e to the x. That's just the sum of x to the k over k factorial. That's just x to the 0 over 0 factorial is 1, plus x to the 1 over 1 factorial is x, plus x squared over 2 factorial, plus x cubed over 3 factorial. This should be one of your favorite power series. And you probably learned in Calc 3, in fact, you most definitely learned in Calc 3, that this series converges for all real x. In particular, plug in x equals minus 1. Well, when x equals minus 1, we get e to the minus 1 is just 1 minus 1, those cancel. Then we'll get 1 over 2 factorial, because minus 1 squared is just the 1. Then we'll have, minus 1 over 3 factorial, because minus 1 cubed is minus 1. Then we'll have plus 1 over 4 factorial, minus 1 over 5 factorial, and we'll keep going. Only here we'll keep going on forever. We use an infinite number of terms. This number, e to the minus 1, which is 1 over e, is the value of this infinite series. And I just used my computer here and computed that. That's approximately 0.367879. That's the 6th decimal place approximation of this number 1 over e, which has this infinite series as its as a series representation. Now, how does that compare with d sub n? Remember, for example, d4 was just 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial. That's a partial sum here in the series for 1 over e. That looks really bad. d5 is just a bigger partial sum, 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial, etc. What this tells us is that d sub n will approach 1 over e as n goes to infinity, because you'll just be getting larger and larger partial sums. And when I say larger and larger, I mean with more terms. The actual sizes of the partial sums go down and then up and then down and then up, etc., because of the alternating nature of this series. Furthermore, d sub n will approach 1 over e very quickly. The convergence is very fast. Why is the convergence very fast? Well, it's because you have an alternating series here, and by the alternating series test, if I look at d sub 4, it will differ from the full value of the series, which is 1 over e, by at most the size of the next term, which is just 1 over 5 factorial. And not only is it an alternating series, so we can tell that the maximum error is less than the size of the next term, but each term has these factorials in the denominator, so they go to 0 very quickly. So let's just look at D4. D4 is just 9. 4 factorial is 24. So if you look at just rearrangements of a 4-letter string with 4 distinct letters, you pick one at random, the probability you get a derangement is 9 over 24, which is exactly 0.375. That's the same as 3/8. Notice how close that is to 1 over e, which is 0.367. Let's say I skipped d5 here, but you could certainly look at that. d6 over 6 factorial is just this number here, and that's 0.368056. That actually gets the first 3 decimal places correct, because the 3 decimal approximation to 1 over e would be 0.368. So you've already got 3 decimal places right. The error is at most 1 over 7 factorial, which is about 1 in 5,000, 1 over 5,040. So we really got a very good approximation just with d6 over 6 factorial, a very good approximation to 1 over e. If we kind of flip things around, let's ask when we might want to ask about this situation. Well, I'll just tell you a real quick story at the end of this talk here, which is now. Let's say you have something like a Secret Santa program. You might be familiar with these things. That's when maybe everybody in an office gets together, or everybody in a class gets together. They all put their names in a hat. The names get mixed up, and then you pick a name at random, and that's a person you buy a gift for. Well, what makes this kind of an annoying thing? Okay, there might be many different things that make it annoying, but the thing that really makes it annoying is if everybody puts their name in a hat, and you pick the name, and you get your own name. Then you're the one who's getting a gift for yourself. Normally what people do is they just exchange or something like that. My question to you is, when people do this, you have a group of people, they all put their names in a hat, they mix it up, and then they all pick one at random. What's the probability that it will be a good Secret Santa arrangement? Meaning nobody gets his own name. Well, nobody getting his or her own name is exactly the same as saying that the rearrangement caused by the mixing up and then drawing randomly the names, that rearrangement of the n people is a derangement. And we can tell that the probability of a derangement is almost exactly 1 over e. I say almost exactly because even with 4 people, you're extremely close to 1 over e. If you have anything more than 6 people, it's going to be 1 over e accurate to within 3 decimal places. So whether it's 6 people or 20 people, the probability that things will work out well, that nobody gets his or her own name back, is only about 1 over e, 0.367879. What does that mean? The probability of a bad Secret Santa distribution, that somebody gets his or her own name, is 1 minus that, which is something like bigger than 0.63. So with a greater than 63% chance, somebody will be stuck with his or her own name. And that will be true with almost the exact same probability, only varying by tiny amounts, no matter how large a group you start with. So for fun, here's what you should do. Try it out. Do an experiment. Get 6 people together. Write down each person write his own names, shuffle them up randomly, pick them out of a hat, and I claim that about 63% of the time, even a tiny bit more than that, somebody will be stuck with his or her own name. And it doesn't matter if it's not 6, it doesn't matter how many people you use, it'll be almost the exact same probability, as you see, always very close to 1 over e. That's a somewhat surprising result, that you get almost exactly that same value. Not exactly, changes a little bit, as these partial sums are slightly different from each other, but almost exactly the same value, and it's 1 over e, that's a very special number, regardless of the size of the